Excellent. Okay, so today we are going to start our last kind of section on induction. Now you might think like we already did that, right? In the last we did, right? We were looking at this idea of electromagnetic induction. But what we're going to look at a little bit further on this week and next week is this idea of mutual inductance, self-inductance, and how inductors right, store energy in a circuit. We won't have time to do it in the regular class. There's a little bit of differential calculus that's involved, but that's the plan. We do a little bit of and I tried to keep the assignments shorter, as I know we're kind of reaching the saturation point. At least I think most students are, right? Reaching the kind of saturation point of knowledge. So 3 questions this week on basically mutual inductance. We'll do an example problem, and then it kind of shows you how you would tackle those 3 questions. And then next week, we'll look at self-inductance and how it stores energy. All right. All right. So I'm going to go ahead. There's a 3-minute video that I posted along with this week 15. And I think I'm off a week on this class just because for whatever reason I counted spring break as a week. All right. So if you see week 15 here and week 14 in the other class, that's why. So, but anyway, you can see here on week 15. Okay. Let me share this for those that are watching online. Try that again. Let's see. We go finish time. We will just work with my set then here. All right. So the one thing that I'd like you to, so we have basically 4 sections, an introduction section, the mutual induction. So we'll do those 2 things, the first top 2 today, and then self-induction, inductors, energy of the magnetic field again will be next week. We're going to spend 3 minutes here though, kind of giving you a short introduction, right? I wouldn't call it an ultimate guide, okay? Even though, because that 3-minute video is probably not an ultimate guide to anything, okay? But I'm sure it got some more clicks on YouTube by naming it that. But it will be a decent intro, right, to what the heck we're thinking about when we're thinking about inductors. And it's also a good reminder of what we've been doing with Lenz's law. And again, let me pause to make sure I got everything set up for our Okay, I think I'm finally ready.
Today, we are going to talk about inductance and inductors. Inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. In our tutorials about electromagnetism, we saw that when an electrical current flows through a wire conductor, a magnetic flux is developed around that conductor. To concentrate.
All right, so you can see there, right, that you're using your right-hand rule. You can see here, right, that you're using your right-hand rule. So if you have your current, right, going from right to left, right, it makes sense that those green circles, right, are the magnetic field, right, in the correct direction.
Concentrate their magnetic flux, we can tightly wrap the wire around a solid central core. Inductance is the ratio of the magnetic flux in the coil divided by the electric current flowing through the coil that produces that flux. This is the most basic form of an inductor. Nothing more than a coil of wire wound around a metal central core.
The interesting thing about that video is it doesn't show metal central core, right? It showed an air core. It was just a coil of wire around a air core. So I know you can't see this in the video, but you're welcome to stop by the lab or catch me after class if you'd like to just see a regular inductor. But this is your inductor on our circuit boards that we've used in lab. It is this yellow piece, okay? And you can just see it as a white wire that leaves the circuit board, goes up through the inductor, wraps around a whole bunch of times, okay? And then it comes back over, eventually making its way over to the black wire that comes down and back to your circuit board. So it is just a loopable insulated wire. And then you typically take a core, right, that has some type of magnetic material to it. So this would probably be like an iron core. You can change the core on your inductor. You could do, depending on what permeability you want, or just basically how strong the magnetic field you would want to be. So you could leave it without a core, or you could take this core and just slide it in right to your particular inductor, just like that. And that's an inductor. It's going to store energy as you change the current. Okay? So it's used a lot it's used in both DC and AC circuits, but for a lot of AC circuits, because you're hearing about how do you do induction, you have to have a change in current. And if you're going to do that, you're going to do that with AC, right? Type of current most often. All right, so imagine on that video, if you're at home, imagine on that video that you had just basically a cylindrical metal core put through that coil of wire.
Here we have a simple circuit. If we turn on the switch, the light bulb will turn on instantaneously. Let's connect an inductor series to this circuit. We know the inductor does not like to change the current through it. Initially, no current flows through the inductor. When we switch on the circuit, the light bulb does not turn on immediately as before. It will increase the brightness gradually. But after a short time, the current will become stable, so the inductor does not show any resistance after that. The inductor also resists the current from switching off instantly. The current won't just stop flowing in the inductor in an instant. So when you switch off the power, the inductor will try to continue the current flow. It does this by quickly increasing the voltage across its terminals. It actually increases so much that you can get a little spark across the pins of your switch. This is because the inductor is a component that resists changes in current. Suppose instead of a switch, we are using a variable resistor to control the current of this circuit. For the explanation, let's assume our resistor can have 4 resistance levels as shown. To measure the current of this circuit, let's attach an ammeter to this. The inductance of this circuit is 0. So as soon as we change the resistance, the current will change instantaneously. We can plot the current of this circuit. Let's compare this with a circuit that has an inductor. Initially, the current of both circuits are equal. But when we change the resistance, the inductor resists the change of current. So the current of circuit B changes slowly. The current will slowly rise to the same level. Thank you for watching us. Like and subscribe for more educational videos.
All right. So from the ultimate guide of inductors, what was our definition of induction? Yes, 2 students that are here today. Hey, good job. It was. I'm truly impressed. I'm not sure I could have done that. I'm watching that video. All right, so current magnetic flux. What was our, let's see here, variable that we use for magnetic flux? There you go, phi, right? Capital P. There you go, there you go. There's our flux. And we're dividing by our current. So one thing that I completely forgot in our algebra-based physics course is to give you a definition for, or units for magnetic flux. Okay, so let's do that real quick. We will again do it tomorrow. What do you remind me to do that tomorrow? That'd be great. Okay. All right, cool. So we got magnetic flux. All right. Remember what our magnetic flux is? It is a magnetic field times an area. And we'll just leave it at that if we just say it's the perpendicular component, right? So we leave off the cosine part. So we think about what the units would be for that. We would have say a Tesla times a meter squared. Or if you don't like to do Tesla times meter squared, you call it a Weber. Not kidding, like the Weber grill. Weber, okay? Of course, named after scientist, Mr. Weber, right? That helped study, right? Inductance. Or in this case, electromagnetic induction, because that's what we are. We're looking at our magnetic flux, okay, the Weber. So if you look at a induction, if we looked at our units for induction over here to the right, we would have we could do two things. We could do either a Tesla times a meter squared over I, or we could just say, if we want to do that value of magnetic flux, we could say that's a Weber divided by I. And both of those, another way you can think of inductance would be to call that a Henry. And, right? And we'll do that with a capital H. Useful, right? Just because if you hear in a problem Weber, okay, I'm looking at magnetic flux. Or if you hear the unit Henry, you are looking at inductance. And so you notice here on this circuit board we have in front of you, you have this inductor is 5 millihenry. Okay? So it is a unit of inductance, how much magnetic flux per current. Right. Good question. Because well, let's see here. I the current, A is the amps. Thank you, Natalie. Thank you. Just put an amps on it there. I really actually enjoy it when students like not trip me up, but correct me, right? It means pay attention, right? I love it. Great, good job. Okay, so T over M, right, divided by A, divided by A. Good, excellent. Now, actually, I did replace one thing that I shouldn't have there, though, right? Is that can be I, right? Because that's just our variable. But our unit would be amps. Very good. Thank you. You could break that amps down a little further too, if you wanted to, right? You could break it down to coulombs per second if you want to go really back down to your kind of base, right? SI units. All right. So very good. I need a little picture though, to think of what the heck's going on here. So we're going to look at the following. Let's say that you took a coil of wire. Okay. And if you wanted to, you could say go around and around and around a couple times and say I have, N number of coils of wire. Okay. And around that, let's say around that particular coil, we have another coil. And again, we could just draw it in terms of a couple times. You could have N around it. So there's two N's, right? So we do N1 and N2. All right. So we'll say number N1, let's say number of coils of wire for the smaller radius loop. Okay. So what do I mean by smaller radius? Well, let's say if we had that value right there, be say R1. Okay. And then so let's define N2. We can say N2, say the number of coils for the larger radius loop. Not great English, should be right. Larger loop, or like the loop with the larger radius. All right, we'll go larger radius loop. So in the center, we say like come out there to there. We can say that's maybe R2. One thing we're going to do though is we're going to take that loop. Oops, did not want to delete that. Darn it. That's all right. We'll do like this. All right. And again, I've kind of drawn it as one. Let me clean that up just a little bit. What's that squiggly line there represent? It kind of look like a wave. Yeah, it looks like sine wave, right? Or it can maybe a cosine wave. It looks like a wave. Okay, that line indicates that it would be a alternating power source. Okay, so like an AC power source. And of course, remember, right, that AC stands for alternating current. Okay. And if we were to think about what that actually is telling us, it's something along the lines of, the current's going in that loop to the right on the outer side. That means the current's going, right? Say basically counterclockwise for a little while. And I'm not going to redraw it, but that means after a certain amount of time, right, it's going to flip and go the opposite direction, right? We have this current that's just going flip-flopping back and forth, back and forth. But at this particular moment, we're drawing it where that current is going in a counterclockwise direction. So what type of magnetic field is being generated in the center of that loop? Let's say actually a better way to ask that, what direction would our magnetic field be at the center of that loop? Yeah, it's coming towards us, right? So we might say in the center of the loop, we could draw maybe some dots. And those dots represent a magnetic field coming towards us. Okay. Let's see what we remember yesterday from Lenz's law. So that means that what I've just drawn there is the dots would represent the magnetic field. So we do a little magnetic field right there, right? Caused from the current running through that outer loop. Okay. That's electromagnetic induction, is it not? Right? That's where you're saying that because I have that current, actually, that's not really electromagnetic induction, right? That's just saying I have a current and I generate a magnetic field, right? Because we know a magnetic field is generated from a moving charge or a current. So as you run that current in a counterclockwise direction around the outer loop, what direction is current generated on the inner loop? Also ask that one more time. So like if you think about the current running around counterclockwise on the outer loop, that is creating the magnetic field that we've drawn on the board, which is coming out towards us. But that is going to induce a current on the inner loop. We've got to think about Lenz's law for this, right? So Lenz's law states that the current that is induced will create a magnetic field that opposes, right, the change in magnetic flux. So what created those dots, right? Created with those dots is the current that is pictured there in green. So that means on the inside of that particular loop, the magnetic flux is changing out towards you. Okay. So what do you have to do? You would have to make a current that would be opposite of that. Okay. In other words, if we were to draw it maybe in a different color, on the inside of, just on the inside, right, of our circle, we would have maybe some X's. And what those X's would represent would be the magnetic field created from the induced current on that inner ring. So what direction is our current then? If you could imagine, again, your right-hand rule, where now you have magnetic field that is opposing. So we have the X's there from the current. So we would have a current that is going around the inner ring in a clockwise direction. All right. So we started out this little lesson here saying our induction is our magnetic flux divided by our current. What we're currently talking about here is what's called mutual inductance. Mutual inductance, okay? And you notice here, right, that picture that we just draw, we got two currents. How do we distinguish between the currents? Would we call that current, the one going around the outer loop, should we call that current 2 or current 1? Current 2, right? It's going around the outer loop. We've done everything else with the outer loop as 2, so we'd say 2 there. And we could say, give a little 1 right there next to the inner current. I think this is good starting out with mutual inductance because it makes you think about like what is induction? It is the resistance, if you will, to changing current. So what do we got to do? We got two ends to choose from. We got two I's to choose from. Okay. So let's think about this the way we've on it, the way we've been talking about. Let's think about this as the induction of the inner ring. Due to current running through the outer ring. Okay, so when we say, well, we're looking at of the inner ring due to the current of I2, right? So we're thinking about, well, we'll put a little I2 right there. Okay. And so we're clear. Let's add another thing on here. Let's take this. Since we're doing mutual inductance, we can think about it like a little M right there. And that would be that guy right there. What about so we have I2, right? That is the current running through the outer loop. That's the thing causing the induced current on the inner loop, right? So this, what else do we need to do? We got N1, we got N2. Let's say we had like an N, this would be N1, right? Number of loops on the inside. And so we could also put a little 1 right there, right? To represent the magnetic flux to that inter loop. Sharing screen or not? What am I sharing here? Let's see. To mutual tokens. Let's see, did I get that right? Yeah, let's see here. Cool. All right, cool. So that's where that came from. Okay, so when you see there on 14-1, okay, our notation is a little different, right? Where it says M21, the mutual induct M21 of coil 2 with respect to coil 1. Okay. But notice the key thing I want you to take on, look on there is on 14-1, how you notice that you have a subscript of a 2 in the numerator, right, after the N, and you have a subscript of a 1 in the denominator after the I. Right? So, so same thing when you look at 14.2, right? You're looking at that inductance M, right? Which is, again, you have a 1 as a subscript after the N, and then you have a 2 after the subscript of the I. If you wanted to see why there's two equations, think about, you could do just a real quick thought experiment and see how you could manage that, right? How could you switch this around? Like, how could you switch this experiment around to create that second equation? Yeah. Yeah. So I don't know if you heard that very well online, but basically you just change where the power source is at connected to. Change your power source and connect it to your smaller ring, right? And then your outer ring would be the one that's getting this inductance type of property to happen to it. Okay. Okay. So lastly, before we do kind of a quick example problem, if you were to look at this and you thought about that magnetic flux, where have we seen that? Or actually the N times the magnetic flux, where the heck have we seen that before? Yeah, EMF, right? So if you look at Faraday's law, we said the EMF, right, was equal to a negative, and we did N times, we didn't really change. Okay, so we did a delta there, right, in your algebra-based physics class, and calc, we replaced that with a little d, right? So you put there like a little d there. Okay? And instead of a delta t, you would replace that with a little dt. All right, so what substitution could you make there? If you wanted to say your induced EMF, right, E, you have N and you have phi. So you have N times the magnetic flux down there. And in the numerator, you have N times a magnetic flux up there. So we could change this around just to say M times I. We said we can leave the subscript if we want to. M times I2 would equal N times our magnetic flux. Again, if I wanted to be a little cleaner with your notation, that magnetic flux there would be the, oh, for us, this one would be the 1, 2, okay? So we can go ahead and add it on there. It's just telling you the magnetic flux of ring 1 as a result of the current running, the alternating current running through 2. All right, so we can make that substitution in there, right? So we just basically, okay, N times L, here we go, okay, that's M. That's the substitution right there, right? Which is to say that your number of coils times your magnetic flux is equal to your inductance times your change, small change in current. Yep. And this is where your notation becomes, that's why I wasn't too particular on the notation, right? Because basically your mutual inductance, right, should be basically the same, right? Where you're looking at defining it in the following two ways. So we've done that. We've kind of have this relationship now for And I guess let's make sure we're clear with our picture that we were working with. Which one I that would be. So if we were to look at this, right? What are we looking at here? That's our mutual inductance. What is this? This is the electric, this is the EMF that's induced in ring 1, right? For us. That's that inner ring. And then we would have, that would be the 2 there for the current. And so how was our current changing in the outer ring that we labeled 2? And how does that create an EMF in the middle ring that we label 1? Okay. So we're going to use some of those 2 equations right here, right, to do A and B. And then we'll spend most of our time in the next 12 minutes or so doing the one that doesn't have an answer already on there. All right. So we're going to go through this next one kind of quickly. But you're going to look at, finding your maximum EMF down here in 14.1. We are just going to look at this one real quick to give us an idea of those 2 equations that we just did, how you might use them. So A, what is the mutual inductance, okay, of the 2 coils? We have some information there. We have a long solenoid, okay? And so let's be real clear about what's happening here. You have the number of coils N2 is the outer ring, just like we did previously on my picture right there on the OneNote, right? And then we have a radius R2. Okay, so we have a certain number of coils of wire there on the larger ring, and it's a long solenoid length. Okay, so we have this solenoid. We did that in lab last week, right? We were dealing with solenoids, okay, with a smaller radius and a certain number of turns. Okay, so what is the mutual inductance of the 2 coils? Okay, more importantly, if N1 is 500 turns, right? N2 is 10 turns. Turns being the number of coils. So we got 500 in that long solenoid. We got 10 in the larger radius coil. R1, smaller at 3.1. We have 75 centimeters. Again, just think to your lab, right? You'd had your slinky there, right? Maybe you had 500 turns over, or 250 turns of that slinky over a meter, right? Here you have 500 turns over 75 centimeters, so about 3/4 of a meter. And the current in the solenoid is changing. So which one are we having our alternating current? We're having it on the inner ring. Okay. So our inner ring is here. And so what is this causing? This is causing a current to flow in the outer ring. This is a little bit opposite what we just had in that derivation there. We just have the current connected to the middle one, and that's causing induction or a current to flow in the outer one. Okay? And it's changing at 200 amps per second. What is the EMF induced in the surrounding coil? So we got to find the M, okay? And then we have to find our EMF, okay, that's induced in that particular coil. So M, right, is equal, right, to our flux over current. And I only got 2 people here, so it's unfair, right? To kind of ask you all of these questions. But how might we think about, and we also had an N here, right? How might we think about which value we're going to use from that problem for N? What we might use for our magnetic flux, what we might use for I. That's the one, right? So our I, so we're thinking about maybe that being something like 200 amps per second, okay? An amp, just because we have it in, what was that? Amps per second, right? That would be current. Cool. Wonderful. Okay, so I think we have our I figured out. What about N? We got two N's to choose from. We got 500 and we got 10. Correct. Excellent. So now in the head, we would do the 10 and 2, right? So we would look at our number of turns that we would look at the end where the inductance is actually happening. Okay. So that would be the outer ring. We got 10. Um, so let's add those in real quick. We got 10. We got 200. We haven't written it up yet, but what is our definition for, well, actually we did. We said our magnetic flux, right, was B times A. Okay. So we have here B times A. How can we find B? That's this magnetism game you play, right? Like, how do we know what our magnetic field would be on the center of that particular solenoid? I'll give you that one. Do you remember? Times current is in there. There's something else in between. Yeah, good. So you got permeability, you got current. That shows up in most of them, right? In terms of like the magnetic equations. Okay. What did you guys calculate when you said you had like 250 turns of a slinky over half a meter? Coil density, right? You said, okay, so if I take this one, if I have 500 turns and I have it over 75 centimeters, right? That's what we're going to put in here. So we're going to put our U, we're going to take it times our, um, right? Current density would be, we have 500. 5. Actually, I should probably write that differently. I need to write it in there. N times I. That's our B. And then our area, well, it's a cross-sectional area, right? So it's a cylinder. So we're looking at a circle, right? So like say pi. We have two R's though. Right, you got two R's right there. And what are we looking at? We're looking at our middle, our little one, right? For a solenoid. So we look at there R1. All right, now we play against some numbers. So 10, we got 4 pi times 10 to the negative 7th amps. We had 500 turns over 0.75 meters. I don't know what we put in for I. Right, that was our comment. Like, what do we put in for I right there? Let's think about that for a second. Okay. We got pi. What was our value for our inner radius? What the heck is that? That was 3.10 centimeters. Okay, so we'll put 0.0310 meters, and we got to square that. Hmm. Yeah, it is. That's what we put on the denominator, right? What do you notice there? Yeah. So you're absolutely 100% correct, Anthony. You said, well, let's put a 200 on there, right? But we put 200 on the bottom, right? Well, where does the magnetic field from the solenoid come from? It comes from the current running through that solenoid, right? Where does the self-induction come from on the second outer loop? It comes from, right, the same exact current running through that inner loop. All right. So yeah, absolutely. Put 200 right there. You'll notice it cancels. Okay, so I at least want to get you started on the second problem because it actually won't take all that long. So yeah, we see it cross out. Okay, so we have an exact representation here. We have N1, N2. Did we include? I think we included that. We had 10 and we also had 500, right? There you go. Okay, so there's your 10 and your 500. So that's good. And then we have, yeah, the eyes cancel out. And we went ahead and just put in the Lang. So we have all of that value right there, right? So that looks perfect. So we get 2.53 times 10 to the negative fifth Henry. 2.53. And the last one's really easy, right? Because you're just looking at the EMF would just be, say, a negative of that mutual inductance value times the DI over DT. So you might have already seen it. If you did, that's fine. But what do we do here? How do we find our max EMF? We have our mutual inductance. We can go ahead and plug that in. 2.53 times 10 to the negative fifth Henry. Times what? 200, right? Exactly right. Say, just take it times your 200, right? Your 200 amps per second. That's what current over seconds is. Amps per second. Wonderful. Okay. And you get, in this case, negative 5.06 times 10 to the negative third. And our unit there, volt. Great. You've worked yourself through an example problem, right? Where you start thinking about this idea that the magnetic field generated in one coil of wire results in the induced current on another wire. Okay. And maybe you have an easier way, right, to find out EMF rather than the other way we've been doing it in class, where you're looking at a change in B, a change in A, or a change in your angle. All right. So again, just to get you an idea, though, I've started on here. Okay, if you have your current right there. So it's building off the same numbers you have on the previous example. It just says a current that's given as a sine wave, okay, flows through a solenoid if part B of example 14.1 was the maximum EMF induced in the surrounding coil. Right, so it's just saying, instead of it just being 200 times per second, right, as your current, it's saying that this is fluctuating according to that sine wave right there. Okay. And you need to find out your maximum EMF, right? So you already know your inductance, 2.53 times 10 to the negative fifth Henrys, because it doesn't depend on current, right? It could be any current running through there. You'd have the same value there for M. So you would call that in the text geometry dependent, right? It doesn't matter what the current is, it just matters the geometries. Next up, so how might I find, in that case, how might I find, if I think about that, what do I have to know? I have to find DI over DT. So, as we're short on time, calculus students, how can we do DI over DT? This is a way zoomed in picture right here, right? Oh, shoot. Seriously. Okay. So this right here, if you think about if you looked at I as a function of time and you had 5 amps times sine of, then what was it, 120 pi times t. Okay. Remember, this part right there is telling you what? On your max amps, right? Or max current. So it's saying this value right here, 5.0 amps. Okay. And it's saying 120 times per second. Remember, this part right here, right, would be equal to 2 pi times your frequency. Right? But my question was, how do you get to di over dt? Excellent. So you're taking the derivative of that function, right? Of I as a function of t with respect to t. Okay. So we're doing di dt, right? With respect to that. So if you were to look at this 120 pi, what you would get, and again, since we're sort of running out of time, we'll go ahead and do it together. You would have 5 amps. And I forgot my unit in here. That would make a lot more sense if we included it. That's radians per second. So 120 pi times radians per second. Let's just make that cleaner. So it's 5 amps. We would then do, say, times 120 pi radians per second times derivative sign. Anybody? Cosine? There might be a negative. I don't remember that part. Okay, there might be a negative there, right? In towards of cosine. Okay. And then everything else will be the same. So you have 120 pi times radians per second. Times t. The key thing here, though, right? Look at your unit right there. Right. That's basically, again, radians is kind of a unitless number. You don't kind of really worry about it. So that's going to be whatever 120 times 5 is. Is that 600? All right, so you got 600, right? Amps per second. Where on this graph on here, this little graph here, am I having my greatest change in current? Right there, right? Okay. So it'd almost be like we would, if we wanted to do a plot of, you know, what, if you said what di over dt looked like, right? What would it be? It'd be, say, like you have a really big peak, right? It would, you would have, what, go up, I don't think I would start, but you would have a peak here. You'd go back down to 0 here. You have a peak there, and then it would go back down here, it'd be 0, so it'd go down to there. Right? And then it'd be negative peak right there. That's actually opposite. You have a what, negative slope right there, right? So if we have a negative slope right there and we did di dt, it's going to have to be a maximum here, goes through 0, comes up to a positive, okay, goes back down to 0. And then we would have basically go up there, that, okay? All right, so what are we looking at? We're looking at that part right there, right? That's why we'd get the negative in there, wouldn't we? There you go. All right, so you'd have right there, right there. This value right here would be the negative, right? 600 per amps per second. Take that times your inductance, right? And you know how your max EMF would be. Well, clear as mud. All right, so there are then 3 questions up there that are included, and they're all in mutual inductance, I believe, 28, 30, 32. Cool. Any questions? Right on. Enjoy learning some physics.